Welcome to the Deep Dive. Today, we're going to be taking a deep dive into the world of black holes.
Oh, yeah.
But not just any black holes.
Right.
We're going to be looking at whether the way they eat or accrete matter is the same for both stellar mass black holes and the supermassive giants that are lurking at the hearts of galaxies.
That's right. And to do that, we'll be looking at some pretty recent data from NASA's IXPE mission,
Okay.
the Imaging X-ray Polarimetry Explorer,
Wow.
which is giving us a completely new way to study these really enigmatic objects by looking at the polarization of X-rays they emit.
Now, you mentioned X-ray polarization, and I have to admit, that sounds pretty complex to me.
Oh, yeah.
Could you break that down for us?
For sure.
How does looking at the polarization of X-rays actually help us understand what's happening around a black hole?
Well, think of it this way.
Okay.
Light, including X-rays, can be polarized, meaning its waves vibrate in a specific direction. You probably have polarized sunglasses, which reduce glare by only allowing light waves vibrating in a certain direction to pass through.
Okay, so it's like filtering the light
Exactly.
to get a clearer picture.
By measuring the polarization of X-rays coming from a black hole system, we can gain insights into the geometry and the structure of the region emitting those X-rays.
Okay.
So that's the area where matter is swirling around and falling into the black hole.
Okay.
It's like having an extra sense to probe these incredibly dense and hot environments.
So we're essentially using the direction of those X-ray waves to map out what's happening around the black hole.
Precisely.
That's pretty incredible.
Yeah.
Now, before we dive into IXPE's observations, let's take a step back and make sure we're all on the same page when it comes to the types of black holes we're discussing.
Okay.
What exactly are stellar mass black holes?
Stellar mass black holes are the remnants of massive stars that have collapsed at the end of their lives. Imagine squeezing several times the mass of our sun into a space smaller than a city.
That's hard to even wrap my head around.
It is pretty extreme.
Yeah.
Then on a completely different scale, we have supermassive black holes.
Okay.
These monstrous objects reside at the centers of most galaxies, including our own Milky Way.
Okay.
They can be millions or even billions of times more massive than our sun.
So we're talking about a massive difference in scale here.
Huge.
Millions, even billions of times.
Right.
It's wild to think that something so small, like a stellar black hole, could share any similarities with something so gargantuan. But maybe I'm getting ahead of myself.
Yeah.
Let's talk about IXPE's findings.
Yeah.
What has it been observing, and what's so surprising about the data?
IXPE has been observing a variety of black holes, both stellar mass and supermassive, and in different states of activity.
Got it.
One of the first objects it studied was Cygnus X1, a well-known stellar mass black hole in our own galaxy.
Cygnus X1, that's one of the most famous black hole systems out there. Right?
It is. Yeah. And IXPE observed it in what we call a hard state, where it's emitting a lot of high-energy X-rays. This is thought to be when a region called the corona, which is a cloud of extremely hot gas surrounding the black hole, is particularly active.
Okay, so the hard state is kind of like the black hole being in a high-energy mode.
Exactly.
Right.
And what IXPE found was that the X-rays coming from Cygnus X1 in this hard state were polarized in a specific way, with the direction of polarization aligning with the direction of its jets. Those powerful beams of particles shooting out from the black hole. This suggests that the corona is actually extended along the black hole's accretion disk, like a donut surrounding the black hole.
So it's not just a blob of hot gas above the black hole, it's more like a flattened ring.
Yes. And that was a bit of a surprise.
Interesting.
Yeah.
So what about the supermassive black holes? I imagine things must be completely different on that scale.
Well, that's where it gets really fascinating. IXPE also observed a supermassive black hole. This one in a galaxy called NGC 4151. And guess what?
What?
They found very similar polarization properties.
Wait, so you're telling me that a black hole millions of times heavier than our sun might have a corona structured similarly to one just a few times heavier?
It does.
That completely changes how we think about these objects.
It suggests that despite their enormous difference in size, the basic physics governing the accretion process and the shape of the corona might be remarkably similar.
Okay, now I'm really hooked.
Okay.
So we've got this stellar mass black hole in our own galaxy. and a supermassive black hole millions of light years away.
Yeah.
And they're showing these surprising similarities.
Yeah, yes.
This is feeling like a unified model of black hole accretion might actually be a real thing.
Yeah.
But I'm guessing it can't be that simple, right?
Right.
There have to be some exceptions.
Yeah.
Some black holes that buck the trend.
You're absolutely right.
Okay.
The universe rarely gives us perfectly neat and tidy answers. While these findings point towards a unified model, there are definitely some intriguing outliers.
Okay.
Take, for instance, Ursinus and NGC 1068.
What's special about those two?
These are what we call obscured black holes.
Okay.
Our view of the central region where the accretion disk and corona are located is blocked by a thick, donut-shaped cloud of gas and dust.
Hold on. What exactly is the system axis in this context?
Oh, yeah, good question.
I'm picturing this donut-shaped cloud.
Okay.
But what does the axis refer to?
The system axis is essentially an imaginary line running through the center of the black hole system,
Okay.
perpendicular to the plane of the accretion disk.
Okay.
Imagine the donut-shaped cloud being aligned around this axis.
Got it. So we can't get a direct view of the central engine.
Right.
Because of this dusty donut.
But what IXPE found was that these obscure black holes have very high polarization.
Okay.
And the direction of polarization is perpendicular to that system axis we just talked about.
Got it.
This means the X-rays we're seeing are actually being scattered off that obscuring cloud.
Oh, I see.
Before reaching us.
It's like we're seeing the black hole shadow or reflection rather than the black hole itself.
That's a great analogy.
Okay.
And here's where things get even more interesting.
Okay.
There's another system, Cygnus X3, which has a similar polarization signature to these obscured black holes, even though we're looking at it almost face-on.
Wow.
This has led researchers to think that Cygnus X3 might actually be much more luminous than we initially thought. But a lot of those X-rays are being absorbed by the material surrounding the black hole.
So it's like we're only seeing the tip of the iceberg with Cygnus X3.
Exactly.
And the true power of its X-ray emissions is hidden.
Then there's another stellar black hole, 4U 163047, which threw us a curveball.
What happened there?
It showed high polarization even in a soft state.
Now you're throwing around hard and soft states.
Right.
Could you explain what those mean?
Sure. Think of it as the black hole's activity level in the hard state, like we saw with Cygnus X1.
Right.
The black hole is emitting a lot of high-energy X-rays.
Okay.
And the corona is thought to be very bright and active in the soft state.
Right.
The black hole is quieter.
Got it.
Emitting lower energy X-rays.
Okay.
And the accretion disk is thought to be more prominent.
Okay, so hard is like a roaring fire.
That's a great way to put it.
And soft is like the embers glowing.
Now, what's unusual about 4U 163047 is that it showed high polarization in the soft state.
Okay.
Which isn't something we usually see.
Right.
This could suggest something interesting is going on with its accretion disk.
Right.
Perhaps a more complex structure or the presence of strong magnetic fields.
So we're seeing a pattern emerging here.
Yes.
But with some intriguing variations.
Right.
It's like black holes have a basic eating style. But they can also put their own individual spin on it.
That's a perfect way to describe it.
Okay.
And this actually leads us into a crucial question about the broader implications of these findings.
Okay.
How does this possible unified model of accretion change our understanding of the relation?
Okay, that's a great bridge to the bigger picture.
Yeah.
I'm all ears.
Okay.
How do supermassive black holes and their feeding habits tie into the grand story of galaxies?
Well, we know that supermassive black holes reside at the centers of most, if not all, galaxies.
Right.
And their growth is intricately linked to the evolution of their host galaxies.
Okay.
As these black holes accrete matter and grow, they release tremendous amounts of energy.
Okay.
This energy can influence the formation of stars, the movement of gas, and even the overall structure of the galaxy.
So it's like a cosmic feedback loop.
Exactly.
The black hole eats, releases energy, and that energy in turn shapes the galaxy around it.
And if this accretion process is truly similar across different sizes of black holes, as IXPE's findings suggest, it means we might be able to use what we learn about stellar black holes in our own galaxy to understand what's happening around supermassive black holes in distant galaxies.
Okay.
It's like having a miniature laboratory right in our cosmic backyard
Yeah.
to study some of the most extreme phenomena in the universe.
That's an incredible thought.
Yeah.
If the physics of black hole feeding are scalable,
right,
it would revolutionize our understanding of galaxy evolution. We could study the jets launched by stellar black holes, for example,
right,
to gain insights into the processes that drive these incredibly powerful jets we see coming from supermassive black holes,
yeah,
stretching millions of light years across intergalactic space.
Precisely.
That's amazing.
But of course, there are still many questions that remain unanswered. We need more observations, especially of supermassive black holes in different states, to further test this unified model and explore the full range of variations that exist.
I can only imagine the amount of data that IXPE and other telescopes will be gathering in the years to come.
Yeah.
This is just the beginning of a whole new era of black hole research.
It is.
But before we get lost in a black hole of speculation, let's take a step back and talk about some of the fundamental questions that still remain unanswered.
Okay.
What are the big mysteries that still keep you up at night?
Well, one of the most fundamental and enduring mysteries is the origin of supermassive black holes.
Yeah.
We know they exist.
Right.
And we know they play a critical role in the evolution of galaxies.
Right.
But how did these behemoths form in the first place?
Yeah, it's mind-boggling to think about an object millions or billions of times more massive than our sun just appear.
It is. Some theories suggest they formed from the collapse of massive gas clouds in the early universe. Others propose they grew from smaller seed black holes, perhaps the remnants of the very first generation of stars.
Got it.
But we still lack definitive evidence.
So it's a cosmic chicken and egg problem.
It is.
Did galaxies form first and then their central black holes grew?
Yeah.
Or did the black holes come first and act as seeds for galaxy formation?
Right.
Or maybe it's some complex interplay between the two.
It's a fundamental question in astrophysics.
Wow.
And closely related to that is the question of how black holes accrete matter so efficiently.
Right.
We observe them growing at incredible rates.
Right.
But the details of how they pull in and swallow matter are still not fully understood.
Seems like with each answer we uncover, even more questions arise.
Yeah.
It's a testament to the vastness and complexity of the universe.
Exactly.
Yeah.
And with new observatories and telescopes coming online, including the James Webb Space Telescope, which can see further back in time than any telescope before it, we're poised to make even more groundbreaking discoveries.
It's an exciting time to be exploring these mysteries, but for now,
Yeah.
we need to take a quick breather.
Okay.
When we come back, we'll wrap up our deep dive with some final thoughts.
All right.
And a question to keep you pondering long after this episode ends. Stay tuned. Welcome back to the deep dive. We've been on quite a journey today, exploring the mind-boggling world of black hole accretion and the possibility that these cosmic giants, regardless of their size, might share a similar feeding process. It's truly a paradigm shift in how we view these objects.
It is, and while IXPE's findings provide compelling evidence for this unified model, there are still so many fascinating avenues to explore.
Right, and that's what makes this field so captivating. There's always another layer to uncover, another mystery to unravel. So as we wrap up our deep dive, what are some of the key questions that still keep you up at night? Where do we go from here in our quest to understand these enigmatic objects?
One area that's really intriguing, and we touched on this briefly earlier, is the role of magnetic fields in black hole accretion. We know they're crucial for shaping the powerful jets we observe blasting out from black holes, and they likely influence the structure and dynamics of the accretion disk as well.
So it's not just gravity pulling stuff in. There are these invisible forces at play shaping the whole process.
Exactly. Magnetic fields can channel and direct the flow of matter and energy around a black hole. They can even tap into the rotational energy of the black hole itself, providing the power for those incredible jets that we see stretching for millions of light years.
Talk about a cosmic power source. But if magnetic fields are invisible, how do we actually study them? How do we know they're there and what they're doing?
That's the challenge. We can't see magnetic fields directly, but we can infer their presence and strength by observing their effects on the matter around a black hole, for example, by analyzing the polarization of light, and particularly X-rays emitted from the accretion disk. We can get clues about the orientation and strength of those magnetic field lines.
So it's like a cosmic detective story. We're using the clues left behind to piece together the full picture.
That's a great way to put it. And as our instruments become more sensitive and we gather more data, we'll be able to paint a more detailed and nuanced picture of how these magnetic fields orchestrate the flow of matter and energy around black holes.
It's amazing how these seemingly simple measurements, like the polarization of X-rays, can reveal so much about the hidden complexities of the universe. But stepping back from the details of accretion for a moment, we talked earlier about the mystery surrounding the formation of supermassive black holes. Are we any closer to understanding how these behemoths came into being in the first place?
It's still one of the biggest open questions in astrophysics, but we are making progress. One exciting area of research is the study of the very first stars and galaxies, which formed just a few 100 million years after the Big Bang. These early giants might hold the key to understanding the origins of supermassive black holes.
So to solve the mystery of the largest black holes, we need to look back to the earliest moments of the universe.
Precisely, with powerful new telescopes like the James Webb Space Telescope, we can peer deeper into the past than ever before, searching for clues about the formation of those first stars and galaxies. We're essentially looking for the seeds of supermassive black holes, trying to understand how they formed and grew in the early universe.
It's mind-blowing to think that these objects we're studying today, these ultimate cosmic drains, might hold the key to unlocking the secrets of the universe's very beginnings. It's a powerful reminder that everything in the cosmos is connected from the smallest scales to the largest.
It is, and that's what makes studying black holes so compelling. It's not just about understanding these fascinating objects themselves. It's about using them as tools to probe the fundamental workings of the universe, to explore questions about gravity, space, and time, and to gain insights into the grand cosmic story that we're all a part of.
Well, I don't know about you, but I feel like my mind has expanded several light years today. This deep dive has been a whirlwind of mind-bending physics and cosmic mystery, and it seems like with every answer we uncover, a dozen more questions arise.
That's the beauty of science. It's a journey of endless exploration and discovery.
Exactly. And before we sign off, I want to leave our listeners with one final thought-provoking question. If black holes truly do eat in a similar way, across such vast scales from stellar mass black holes to supermassive giants, does that suggest a deeper connection between the smallest scales of the universe, the realm of quantum mechanics, and the largest scales of the cosmos, the realm of galaxies and superclusters? Is there a fundamental unity underlying all of existence? It's something to ponder as we continue to explore these enigmatic objects and the universe they inhabit.
It's a profound question, and one that we may not have the answer to for generations to come, but that's the beauty of it all, the mystery, the endless pursuit of knowledge, the drive to understand our place in this vast and complex universe.
And on that note, we've reached the end of our deep dive, but the exploration doesn't end here. Keep those questions coming, keep those minds open, and we'll see you next time for another journey into the heart of something fascinating.